Welcome to this fascinating exploration of the science behind cooking borscht. We're going to dive deep into the physics, chemistry, and thermodynamics that transform raw ingredients into this delicious soup. First, let's understand what borscht is. It's a traditional Eastern European soup made primarily from beets, vegetables, and often meat. But more importantly for us, it's a complex system involving heat transfer, phase transitions, and chemical reactions. These are our main ingredients. Each one will undergo fascinating transformations as we cook. When we cook borscht, we're dealing with three fundamental modes of heat transfer. Let's examine each one. Conduction is heat transfer through direct contact. When the pot touches the stove, heat conducts from the burner through the metal pot bottom. This is Fourier's law of heat conduction. Q is the heat flux, K is thermal conductivity, A is area, and dt over dx is the temperature gradient. For a typical stainless steel pot, the thermal conductivity is about 16 watts per meter Kelvin. This means heat conducts fairly well through the pot. Convection is heat transfer through fluid motion. This is the dominant mechanism inside the soup. Hot liquid at the bottom rises due to lower density, while cooler liquid at the top sinks. This creates circulation patterns called convection currents. Newton's law of cooling describes convection. H is the convection coefficient, A is surface area, Ts is surface temperature, and T infinity is the bulk fluid temperature. For boiling water, the convection coefficient ranges from 2,500 to 25,000 watts per meter squared Kelvin, depending on how vigorous the boiling is. Radiation is heat transfer through electromagnetic waves. This is usually negligible in soup cooking, but let's mention it for completeness. The Stefan-Boltzmann law governs radiation. Epsilon is emissivity, sigma is the Stefan-Boltzmann constant, and temperatures are raised to the fourth power. For soup cooking, radiation contributes less than 1% of total heat transfer, so we can safely ignore it. Now let's talk about one of the most important phenomena in cooking, boiling. What exactly happens when water boils? At standard atmospheric pressure of 101.3 kilopascals, water boils at 100 degrees Celsius or 212 Fahrenheit. The latent heat of vaporization for water is 2257 kilojoules per kilogram. This is the energy required to convert liquid water to steam at constant temperature. Here's a question. Why does this matter for cooking? The answer is that once water reaches boiling point, adding more heat doesn't increase temperature. Instead, that energy goes into phase change. This graph shows temperature versus time. Notice the plateau at 100 degrees. No matter how much heat you add, temperature stays constant during boiling. Let's do a quantitative analysis. How much energy does it take to make borscht? We need to heat water from room temperature to boiling. The fundamental equation for sensible heat is Q equals mc delta T. Q is heat energy, m is mass, C is specific heat capacity, and delta T is temperature change. The specific heat of water is 4.18 kilojoules per kilogram Kelvin. This is one of the highest specific heats of any common substance. Let's say we're making 3 liters of borscht starting with water at 20 degrees Celsius room temperature, and we want to bring it to 100 degrees boiling. 3 kilograms times 4.18 times 80 degrees equals 1,003 kilojoules, or about 1 megajoule of energy. If your stove burner is 2,000 watts, that's 2 kilojoules per second. 1,000 divided by 2 is 500 seconds, or about 8 to 9 minutes, assuming perfect efficiency. Of course, efficiency is never 100%. Heat escapes to the surroundings, so in reality it takes 12 to 15 minutes. Now let's talk about the chemistry. What happens to vegetables when we cook them? Vegetables have cell walls made of cellulose and pectin. These are complex polysaccharides that give vegetables their rigid structure. Before cooking, cells are tightly packed and rigid. After cooking, the structure breaks down and becomes soft and pliable. The activation energy for pectin breakdown is 50 to 80 kilojoules per mole. This is why cooking at higher temperatures speeds up the softening process. The Arrhenius equation tells us reaction rate. K is rate constant, A is pre-exponential factor, EA is activation energy, R is gas constant, and T is absolute temperature. Due to the exponential relationship, even small temperature increases dramatically speed up reactions. This is why pressure cookers work so well. If you sauté onions or meat before adding to borscht, You're taking advantage of the Maillard reaction. What is this? The Maillard reaction is a non-enzymatic browning reaction between amino acids from proteins and reducing sugars. It creates hundreds of flavor compounds. This reaction requires temperatures above 140 to 165 Celsius, which is why it only happens during dry cooking methods like sautéing, not in boiling water. The chemistry is complex, but simplified. Amino acids plus sugars yield melanoidins and hundreds of volatile flavor compounds. Let's talk about the beautiful red color of Borscht. This comes from Betalain pigments and beets. What's special about these molecules? Betalains are water-soluble, nitrogen-containing pigments. They're unique to certain plant families, including beets. The red-violet color comes from beta-cyanins. The main one is betalain, which has a maximum absorbance around 538 nanometers. When you heat beets in water, the cell membranes break down and betalain pigments leach into the surrounding liquid, giving the soup its characteristic color. Here's an interesting fact. Betalains are pH sensitive. They're most stable and most red at pH values between 4 and 7. This is why many borscht recipes call for vinegar or lemon juice. The acid helps maintain the bright red color and prevents degradation. As vegetables cook, we're also witnessing osmosis and diffusion. These are fundamental transport phenomena. Diffusion is the spontaneous movement of molecules from regions of high concentration to low concentration. Fick's law describes this. Fick's first law. J is diffusion flux, D is diffusion coefficient, and dC over dx is concentration gradient. As vegetables cook, flavor molecules diffuse out of the cells into the surrounding broth. This is how the soup develops its complex flavor profile. Osmosis is the movement of water across semi-permeable membranes. When you add salt to the pot, it creates an osmotic gradient. Van't Hoff equation for osmotic pressure. Pi is osmotic pressure, I is Van't Hoff factor, M is molarity, R is gas constant, T is temperature. Salt in the broth creates osmotic pressure that draws water out of vegetable cells, which concentrates flavors inside the vegetables while releasing some into the broth. Different ingredients have different thermal properties. Let's compare them quantitatively. This table shows the thermal properties of different ingredients. Notice that water has the highest specific heat, meaning it requires the most energy to heat up. Water's high specific heat is actually beneficial for cooking. It acts as a thermal buffer, preventing rapid temperature fluctuations and ensuring even cooking. What if we use a pressure cooker for borscht? This changes everything thermodynamically. Let's analyze this. The relationship between pressure and boiling point is given by the Clausius-Clapeyron equation. dP over dt equals L versus over T times delta 5. This tells us how vapor pressure changes with temperature. In a typical pressure cooker at 15 psi gauge pressure, water boils at 121 degrees Celsius instead of 100. This 21-degree increase reduces cooking time by 40 to 70% because reaction rates increase exponentially with temperature. As a rough rule, every 10-degree temperature increase halves cooking time, so 20 degrees increase reduces time to about 1/4. An important consideration: how does cooking affect nutrients? Many vitamins are heat sensitive. Vitamin C degradation follows first-order kinetics. This means the rate of degradation is proportional to concentration remaining. The differential equation is dC over dt equals negative kc. This integrates to exponential decay. C at time t equals C0 times e to the negative kt. C0 is initial concentration, K is rate constant. At 100 degrees, the rate constant for vitamin C degradation is about 0.03 per minute. After 20 minutes of boiling, about 55% of vitamin C remains. E to the negative 0.6 equals approximately 0.55. This is one reason we shouldn't overcook vegetables. The longer you cook, the more nutrients you lose exponentially. Let's estimate how long it takes heat to penetrate into a piece of vegetable. This involves solving the heat equation. The heat equation. Alpha is thermal diffusivity. This is a partial differential equation that describes how temperature evolves in space and time. Thermal diffusivity equals thermal conductivity divided by density times specific heat. For a beet, thermal diffusivity is about 1.4 times 10 to the negative 7 meters squared per second. The characteristic timescale is t approximately L squared over alpha, where L is the characteristic length. For a 2 centimeter beet cube, L is 0.01 meters. L squared over alpha gives about 500 seconds, or 8 to 9 minutes. This theoretical prediction matches real cooking experience. Small vegetable pieces cook in about 8 to 10 minutes of boiling. Let's briefly discuss fluid mechanics. When soup boils, what kind of flow do we have? The Reynolds number characterizes flow. Rho is density, v is velocity, L is length scale, mu is dynamic viscosity. When Reynolds number is less than 2000, flow is laminar and smooth. When Reynolds number exceeds 4000, flow becomes turbulent and chaotic. In boiling soup, with rising bubbles and convection currents, Reynolds number is around 10,000. This is highly turbulent flow. Turbulence is actually beneficial because it enhances mixing and heat transfer coefficients by factors of 10 to 100 compared to laminar flow. Let's talk about the bubbles that form during boiling. What determines their size and behavior? For a bubble to form, the pressure inside must overcome both atmospheric pressure and surface tension. The Laplace pressure equation. Delta P equals 2 gamma over R. Gamma is surface tension, R is bubble radius. At 100 degrees Celsius, water's surface tension is 0.059 newtons per meter. For a 1 millimeter radius bubble, the excess pressure due to surface tension is 2 times 0.059 divided by 0.001, which equals about 120 pascals. This is why nucleation sites on the pot surface are important. They provide locations where bubbles can form more easily. From a practical standpoint, let's talk about energy efficiency. How much of the stove's energy actually goes into cooking? A typical gas stove is only about 40% efficient. 60% of the energy escapes as waste heat. Electric stoves are more efficient at 65 to 75%. Induction cooktops are the most efficient at 85 to 90% because they heat the pot directly through electromagnetic induction. Here's a simple tip. Using a lid traps heat and reduces evaporation, improving efficiency by 20 to 30%. After cooking, we need to think about cooling. Food safety depends on temperature control. The food safety danger zone is 4 to 60 degrees Celsius. Bacteria multiply rapidly in this range. At 37 degrees Celsius, body temperature, many bacteria double every 20 to 30 minutes. Bacterial growth is exponential. N at time t equals N0 times 2 to the power of T over Td, where Td is doubling time. For food safety, leftover borscht must be cooled below 4 degrees Celsius within 2 hours to minimize bacterial growth. Cooling follows Newton's law of cooling. The rate of temperature change is proportional to the temperature difference with surroundings. dT over dt equals negative h times quantity T minus T ambient. This gives exponential decay of temperature. Let's summarize all the physics and chemistry we've covered in cooking borscht. Heat transfer occurs primarily through conduction in the pot and convection in the liquid. Boiling creates a temperature plateau at 100 degrees, where energy goes into phase change rather than temperature increase. Cooking involves chemical reactions that break down cellulose and pectin, softening vegetables. Diffusion moves flavor molecules from vegetables to broth, while osmosis affects water distribution. All chemical reactions, including nutrient degradation and structural breakdown, follow Arrhenius kinetics with exponential temperature dependence. Turbulent convection currents ensure even cooking and efficient heat distribution throughout the pot. What are the practical implications of all this science? Because heat penetration timescales, with length squared, cut vegetables into uniform sizes so they all finish cooking simultaneously. Always use a lid when bringing water to boil to reduce energy waste and cooking time. Add vinegar or lemon juice to stabilize Betalain pigments and maintain that beautiful red color. Remember that vitamin degradation is exponential, so minimize cooking time once vegetables are tender. After cooking, cool leftovers quickly by dividing into smaller containers or using an ice bath to minimize time in the danger zone. Cooking borscht is a beautiful example of applied thermodynamics, transport phenomena, and chemical kinetics. Every step, from heating water to softening vegetables to extracting flavors, is governed by fundamental physical and chemical principles. Understanding the science doesn't diminish the art of cooking. Rather, it gives us tools to predict outcomes, troubleshoot problems, and optimize our techniques. Next time you cook, remember that you're conducting a complex experiment involving heat transfer, mass transport, and chemical reactions. How amazing is that?